What if I told you that one planet can float on water while another rains diamonds from the sky? Today we're taking a thrilling journey through the planets in our solar system, from scorching worlds to frozen giants. Each planet has secrets that sound like science fiction, but they're real. Which planet do you think is the strangest? Welcome to Behind the Space. Today we're embarking on an epic voyage through our solar system, exploring every major planet from the scorched surface of Mercury to the icy blue depths of Neptune. We'll discover recent groundbreaking findings that are reshaping everything we thought we knew about our planetary neighbors. We'll uncover mysteries that have puzzled scientists for decades and learn about the cutting-edge missions that are bringing us closer than ever to understanding these distant worlds. This isn't just a tour through space, it's a journey through time itself, back to the violent birth of our solar system 4.5 billion years ago. The birth of worlds, how our solar system formed. Before we meet the planets themselves, we need to understand their origin story. About 4.6 billion years ago, in a quiet corner of the Milky Way galaxy, something extraordinary was about to happen. A massive cloud of gas and dust, what astronomers call a molecular cloud, was floating through space, minding its own business. This cloud was enormous, stretching across light years of space, composed mostly of hydrogen and helium left over from the Big Bang, sprinkled with heavier elements forged in the hearts of ancient stars that had lived and died long before. Then something disturbed this cosmic equilibrium. Perhaps a nearby supernova sent shockwaves rippling through space. Perhaps the cloud simply reached a critical density. Whatever the trigger, the cloud began to collapse under its own gravity. As it contracted, it started spinning, and like a figure skater pulling in their arms, the rotation accelerated. The cloud flattened into a disk, the protoplanetary disk, with a hot, dense center that would eventually ignite to become our Sun. Within this swirling disk of gas and dust, tiny particles began sticking together. Microscopic grains of ice and rock collided at gentle speeds, adhering through electrostatic forces. These pebbles grew into boulders, boulders into mountains, mountains into planetesimals, objects ranging from a few kilometers to hundreds of kilometers across. This process, called accretion, was happening throughout the entire disk. Near the forming Sun, where temperatures soared to thousands of degrees, only rock and metal could survive. These materials condensed into what would become the rocky terrestrial planets: Mercury, Venus, Earth, and Mars. But farther out, beyond what astronomers call the frost line, roughly where the asteroid belt is today, temperatures were cold enough for water, methane, and ammonia to freeze into ice. Here there was much more material to work with. Rocky cores formed first, but once they reached about 10 times Earth's mass, their gravity became strong enough to capture and hold on to the surrounding hydrogen and helium gas. These cores gorged themselves on gas, growing into the massive giants we know today, Jupiter and Saturn. Even farther out, Uranus and Neptune formed in a similar way, but the disk was so sparse at these distances that they captured less gas and retained more of their icy character, earning them the designation ice giants. This entire process took somewhere between 10 and 100 million years, a blink of an eye in cosmic terms. The young solar system was a violent, chaotic place. Planetesimals crashed into each other at devastating speeds. Some collisions were gentle enough to result in growth. Others were so violent they shattered both bodies into fragments. The asteroid belt between Mars and Jupiter represents the debris from this era, a field of rubble that never coalesced into a planet, stirred up by Jupiter's immense gravitational influence. The early planets migrated through the disk, pushed and pulled by gravitational interactions with the remaining gas, and with each other. Jupiter probably formed farther from the Sun than it is now, and spiraled inward before being pushed back out again by Saturn. This migration likely sent a cascade of icy bodies from the outer solar system plunging inward, bombarding the inner planets in what's known as the Late Heavy Bombardment, about 4 billion years ago. These impacts delivered water and organic molecules to Earth, possibly seeding the conditions that would eventually give rise to life. Understanding this formation process helps us appreciate just how remarkable each planet is. They're not just random balls of rock and gas, they're time capsules, preserving clues about our solar system's tumultuous youth. With that context established, let's begin our journey, starting with the planet closest to our stellar furnace. Mercury, the swift messenger at the edge of hell. Mercury is a world of extremes that would humble even the most extreme environment on Earth. This tiny world, barely larger than our moon, occupies the unenviable position of being the closest planet to the Sun, and that proximity has shaped every aspect of its character. Imagine standing on Mercury's scorched, crater-pocked surface at local noon. The Sun hangs in the sky nearly 3 times larger than it appears from Earth, a blazing furnace dominating the heavens. The temperature around you would reach a blistering 430 degrees Celsius, hot enough to melt lead, hot enough that the very rocks beneath your feet radiate heat like a planetary oven. But here's where Mercury gets truly bizarre. Wait 12 hours for sunset, and you'd witness temperatures plunging to a bone-chilling negative 180 degrees Celsius. This is the most extreme temperature swing experienced by any planet in our solar system, over 600 degrees Celsius between day and night. The reason for this wild fluctuation lies in Mercury's lack of any substantial atmosphere to trap and redistribute heat. What little atmosphere exists is so tenuous that scientists call it an exosphere, more of a surface-bounded cloud of atoms than a true atmosphere. It consists of atoms blasted off the surface by solar wind and micrometeorite impacts, oxygen, sodium, hydrogen, helium, and potassium, existing at pressures trillions of times thinner than Earth's air. Mercury's relationship with time is equally strange. The planet completes one orbit around the Sun every 88 Earth days, but it takes 59 Earth days to rotate once on its axis. This 3-to-2 resonance between Mercury's orbital period and rotational period creates a peculiar situation. If you could stand on Mercury's surface, you'd experience a day from sunrise to sunrise. That lasts 176 Earth days, exactly 2 Mercurian years. Even stranger, there are 2 points on Mercury where the Sun would appear to rise partway above the horizon, reverse direction and set, then rise again, all over the course of the same Mercurian day. This cosmic dance is a direct result of Mercury's highly elliptical orbit combined with its unusual rotation. When we look at Mercury through powerful telescopes, it appears as a pockmarked, moon-like world, and for good reason. Mercury's surface is among the oldest in the solar system, a museum of ancient impacts dating back billions of years. The largest of these scars is the Caloris Basin, a massive impact crater stretching 1,550 kilometers across, nearly half the diameter of the entire planet. The impact that created Caloris was so violent that it sent shockwaves through the entire planet. On the exact opposite side of Mercury from Caloris, we find the weird terrain, a chaotic landscape of jumbled hills and valleys created when seismic waves from the Caloris impact converged at Mercury's antipode with enough force to fracture and disrupt the surface. But Mercury isn't just an oversized asteroid. Deep beneath its battered crust lies one of the most surprising features of the solar system. Mercury possesses a massive iron core that accounts for roughly 60% of the entire planet's volume. For comparison, Earth's core makes up only about 15% of our planet's volume. This disproportionately large core has puzzled scientists for decades. How did such a small planet end up with such a relatively enormous metallic heart? Several theories attempt to explain this mystery. Perhaps Mercury formed from particularly metal-rich building blocks in the inner solar system. More dramatically, perhaps, the young Mercury was struck by a massive planetesimal that stripped away much of its rocky mantle, leaving behind the dense metallic core. Or perhaps the infant sun was hot enough to vaporize and blow away Mercury's outer silicate layers, leaving the dense core behind like a kernel within a husk. Each hypothesis tells a different story about the solar system's violent youth, and we still don't know which one is correct. This enormous core gives Mercury another unexpected feature, a magnetic field. Before the Mariner 10 spacecraft flew by in 1974, scientists assumed Mercury would be magnetically dead after all. Such a small planet should have cooled completely long ago, and you need a molten, electrically conductive core generating a dynamo to produce a planetary magnetic field. Yet Mercury surprised everyone. It does have a magnetic field, though it's about 1% as strong as Earth's. This field creates a mini magnetosphere around the planet, a bubble that deflects some of the relentless solar wind streaming out from the sun. Without it, Mercury's already tenuous atmosphere would be stripped away even faster. Recent discoveries have only deepened the mystery surrounding Mercury. The European and Japanese Bepi-Colombo mission is currently on its way to Mercury, having completed 6 flybys as of January 2025, with arrival at Mercury orbit scheduled for 2026. Even during these brief flybys, Bepi-Colombo has returned stunning data. The spacecraft's instruments detected sodium, oxygen, and potassium ions being ejected from Mercury's surface material, literally being blasted off the planet by the solar wind and micrometeorite impacts. The mission also mapped Mercury's magnetic landscape in unprecedented detail during just 30 minutes of flyby time, revealing a complex magnetosphere with shock boundaries, plasma sheets, and magnetic horns streaming away from the planet. Scientists have also discovered that Mercury is still shrinking. Like many baked goods cooling from the oven, Mercury has been contracting as it loses heat over its 4.5 billion-year lifetime. This shrinkage has created enormous cliff-like scarps called roops that crisscross the planet's surface, some stretching for hundreds of kilometers and towering over a kilometer high. These thrust faults formed as Mercury's interior cooled and contracted, forcing the crust to buckle and fold like a grape shriveling into a raisin. And here's one final surprise. Despite Mercury's proximity to the Sun, radar observations have revealed bright patches at the planet's poles that could be water ice. How is this possible on a world that gets hot enough to melt lead? The answer lies in Mercury's axial tilt, or rather, its lack of one. Mercury's axis is almost perfectly perpendicular to its orbital plane, meaning that the floors of deep craters near the poles never see sunlight. In these permanently shadowed regions, temperatures stay perpetually below -170 degrees Celsius, cold enough to trap and preserve water ice. possibly delivered by comet impacts billions of years ago. Finding water on Mercury would be like finding a snowball in the devil's kitchen. Improbable, but apparently real. Mercury is a world that defies expectations at every turn. This scorched, ancient, metal-rich remnant of planetary formation holds secrets about the solar system's earliest days. When Bepi Colombo enters orbit in 2026 and begins its detailed reconnaissance, we'll finally get answers to questions we've been asking since Mariner 10's brief encounters half a century ago. But for now, Mercury remains what it has always been. A small world living on the edge of hell, yet somehow maintaining a stubborn hold on existence in the most inhospitable neighborhood in the inner solar system. Venus, Earth's beautiful but deadly twin. If Mercury is hell, then Venus is super hell with a suffocating blanket thrown over the top. Venus has captured human imagination for millennia. Ancient civilizations watched this brilliant point of light in the twilight sky and named it after their goddess of love and beauty, Venus to the Romans, Aphrodite to the Greeks. It's easy to see why. Venus is often the brightest object in the night sky after the moon. A dazzling beacon that appears as the evening star or morning star depending on where it is in its orbit. Through even small telescopes, Venus appears as a brilliant, featureless orb shrouded in thick clouds that reflect sunlight with astonishing efficiency. For a long time, these clouds fueled romantic speculations. Perhaps beneath them lay tropical rainforests and swamps, teeming with primitive life. Perhaps Venus was a younger version of Earth, still in its Carboniferous period, with giant ferns and dinosaur-like creatures roaming steamy jungles. Science fiction writers of the early 20th century populated Venus with exotic civilizations, prehistoric monsters, and alien jungles. Reality, as it turned out, was far stranger and more hostile than any fiction. In terms of size and mass, Venus truly is Earth's twin. With a diameter of about 12,104 kilometers, Venus is only slightly smaller than Earth's 12,742 kilometers. Its mass is about 82% that of Earth. If you could somehow stand on Venus's surface, you'd weigh almost the same as you do on Earth. The two planets even formed in similar regions of the protoplanetary disk, from similar materials. Yet somewhere along the way, these twin worlds diverged dramatically in their evolution, with Venus becoming the toxic hellscape it is today, while Earth became a haven for life. Let's talk about Venus's atmosphere, because it's unlike anything else in the solar system. The atmospheric pressure at Venus's surface is 92 times that of Earth's, equivalent to being nearly a kilometer underwater in Earth's oceans. The atmosphere is almost entirely carbon dioxide, about 96.5%, with clouds of sulfuric acid floating in the upper reaches. Yes, you read that correctly. The clouds on Venus are made of battery acid. These clouds are so thick and reflective that they bounce back about 70% of the sunlight that hits them, which is why Venus looks so brilliant from Earth and why we could never see the surface through telescopes. But here's the really nightmarish part. This thick blanket of carbon dioxide creates the most extreme greenhouse effect in the solar system. Solar radiation passes through the atmosphere relatively easily, warming the surface. But when that heat tries to radiate back into space as infrared radiation, the carbon dioxide traps it, causing temperatures to build up to staggering levels. The surface temperature on Venus averages around 464 degrees Celsius, hotter than Mercury, despite being nearly twice as far from the Sun. This heat is so intense, and the atmosphere so efficient at distributing it, that there's virtually no temperature difference between the day side and night side of the planet, or between the equator and the poles. It's an oven that never cools down. In this hellish environment, lead doesn't just melt, it would puddle and flow like water. The surface is hot enough to make many rocks glow a dull red in the darkness. The Soviet Venera landers that successfully touched down on Venus in the 1970s and early 1980s were built like armored tanks, designed to withstand the crushing pressure and searing heat. Even so, the longest any of them survived was about 2 hours before succumbing to the hostile environment. Those precious minutes gave us our first and only direct images from Venus's surface, a rocky, forbidding landscape of flat slabs and sharp-edged stones, lit by an eerie orange glow from sunlight filtering through the thick atmosphere. Venus rotates on its axis incredibly slowly and in the opposite direction from most planets in the solar system, what astronomers call retrograde rotation. While Earth completes one rotation in 24 hours, Venus takes 253 Earth days to rotate once. Even more bizarrely, Venus completes one orbit around the Sun, its year, in only 225 Earth days. This means that on Venus, a day is longer than a year. If you could survive on Venus's surface, which you absolutely couldn't, you would see the sun rise in the west and set in the east, and the leisurely progression from sunrise to sunset would take longer than an entire Venusian year. What caused Venus's retrograde rotation? The leading hypothesis suggests that during the solar system's chaotic youth, Venus was struck by one or more massive planetesimals that essentially flipped the planet upside down. The collision would have been catastrophic, potentially vaporizing much of Venus's crust and upper mantle, and causing the planet to re-solidify with its rotation reversed. Such an impact might have also contributed to Venus's lack of a magnetic field. Unlike Earth, which has a strong magnetic field generated by a liquid iron outer core, Venus appears to have no global magnetic field at all, leaving it vulnerable to the solar wind stripping away its upper atmosphere. Here's where the story gets even more intriguing. Venus wasn't always this way. Recent research suggests that Venus might have once been habitable, with liquid water oceans covering much of its surface for perhaps the first 2 billion years of its existence. Computer models indicate that if early Venus had been rotating slowly as it does today, and if it had the right amount of water and land distribution, clouds could have shielded the surface from the sun's heat, keeping temperatures moderate enough for liquid water to exist. Venus could have been the solar system's first habitable planet, perhaps even before Earth became habitable. So what went wrong? The answer likely involves a runaway greenhouse effect, and it's a cautionary tale relevant to Earth's current climate challenges. As the young sun gradually brightened over millions of years, Venus received more and more solar radiation. This caused more water to evaporate from the oceans. Water vapor is itself a powerful greenhouse gas, so this increased the greenhouse effect, which raised temperatures further, which caused even more water to evaporate. This vicious cycle continued until all of Venus's water was in the atmosphere. At these extreme temperatures, water molecules in the upper atmosphere were broken apart by ultraviolet radiation from the sun. The hydrogen escaped to space while the oxygen combined with surface rocks. Without water to dissolve carbon dioxide and lock it away in carbonate rocks as happens on Earth, all the CO2 from volcanic eruptions accumulated in the atmosphere. Venus's climate spiraled into the hellish state we see today. Making matters worse, Venus lacks plate tectonics, the geological process where pieces of a planet's crust move around, recycling material between the surface and interior. On Earth, plate tectonics helps regulate the carbon cycle, with carbon dioxide being pulled into the mantle through subduction zones. Venus's crust appears to be a single solid shell, more like a stagnant lid, without active recycling of the crust. Pressure and heat built up in the interior until about 300 to 500 million years ago. The entire surface may have undergone catastrophic resurfacing. Volcanic eruptions on a global scale released vast amounts of lava that covered most of the planet, erasing older features and creating the relatively young surface we see today. Evidence for this comes from impact craters. Venus has remarkably few of them, and they're all relatively young, suggesting the entire surface was wiped clean in geologically recent times. The upper atmosphere of Venus holds another surprise: superrotation. The thick clouds circle the entire planet every 4 Earth days, much faster than the planet itself rotates. These high-altitude winds can reach speeds of 360 kilometers per hour, faster than the strongest hurricanes on Earth. The mechanism driving this superrotation isn't fully understood, but it's clearly an important part of how Venus's atmosphere circulates heat from the day side to the night side. In September 2020, scientists announced a controversial discovery that reignited interest in Venus: the detection of phosphine gas in Venus's upper atmosphere. On Earth, phosphine is primarily associated with biological processes or industrial production. The detection suggested the tantalizing possibility of aerial microbes floating in Venus's cloud layers, where temperatures and pressures are actually fairly Earth-like. However, this finding has been heavily debated, with some scientists questioning whether phosphine was truly detected or whether non-biological processes could explain it. Regardless of the controversy, it reminded us that Venus, despite its hellish surface, might still hold surprises. Venus offers us a profound lesson about planetary evolution. 2 worlds, born as twins from the same cosmic material, diverged to take dramatically different paths. Understanding what happened to Venus isn't just about satisfying curiosity. It's about understanding the factors that make a planet habitable or hostile. As we continue to discover exoplanets around other stars, many of them Venus-sized worlds orbiting in their star's habitable zone, we need to know: will they be life-bearing Earths or furnace-like Venuses? The answer may determine whether life is common in the universe or heartbreakingly rare. Venus is beautiful from a distance but deadly up close. A brilliant jewel hiding a heart of fire and poison. It's a world that could have been our sister, but instead became our evil twin, showing us what Earth might have become under slightly different circumstances. It's a reminder that our own planet's habitability is more fragile than we might like to believe, and that the balance between paradise and hell can be tipped by factors we're only beginning to understand. The pale blue dot, that changed everything. We live on Earth, so it's easy to take it for granted. But step back for a moment and consider our planet with the same sense of wonder we bring to studying distant worlds. Earth is the third rock from the Sun, a modest-sized world of continents and oceans, sitting at just the right distance for liquid water to exist on its surface. But Earth is far more than a lucky rock in the right orbit. It's a dynamic, living system, the only place in the universe where we know for certain that life exists. Earth's average distance from the Sun is about 150 million kilometers. A distance so convenient that astronomers use it as a standard unit of measurement called an astronomical unit, or AU. This distance places us in what scientists call the habitable zone, or Goldilocks zone. Not too hot, not too cold, but just right for liquid water. The distance alone doesn't guarantee habitability. Venus, remember, isn't that much closer to the Sun, yet it's a toxic oven. Mars is just outside the habitable zone's outer edge, yet it's a frozen desert. What makes Earth special isn't just its location. It's the complex interplay of factors that work together to maintain conditions suitable for life. Let's start with water. About 71% of Earth's surface is covered by oceans, with an average depth of about 3.7 kilometers. The oceans contain roughly 1.35 billion cubic kilometers of water, enough to cover the entire planet to a depth of 2.7 kilometers if the surface were perfectly smooth. This water is constantly moving, driven by temperature differences, salinity gradients, and Earth's rotation, creating ocean currents that act like a planetary circulatory system, distributing heat from the equator toward the poles. The oceans absorb heat during the day and release it at night, moderating temperature swings. They also absorb enormous amounts of carbon dioxide, helping to regulate our climate through a complex cycle involving living organisms, chemical reactions, and geological processes. Earth's atmosphere is equally remarkable. Unlike Venus's crushing carbon dioxide atmosphere or Mars's wispy one, Earth has a nitrogen-oxygen atmosphere at a pressure that's comfortable for life as we know it. About 78% nitrogen, 21% oxygen, and trace amounts of argon, water vapor, carbon dioxide, and other gases. Our atmosphere serves multiple crucial functions. It provides the oxygen that animals breathe and the carbon dioxide that plants need for photosynthesis. It shields the surface from harmful solar and cosmic radiation. It creates weather patterns that distribute water across the continents. It moderates temperature through the greenhouse effect, enough to keep us warm but not so much that we become Venus. That oxygen content is particularly noteworthy. When Earth formed 4.5 billion years ago, its atmosphere contained no free oxygen. The early atmosphere was probably a reducing mixture of nitrogen, carbon dioxide, methane, and ammonia, with no oxygen to speak of. The oxygen we breathe today is a gift from life itself. About 2.5 billion years ago, photosynthetic cyanobacteria began producing oxygen as a waste product. At first, this oxygen reacted with dissolved iron in the oceans, creating vast deposits of iron ore that we mine today. Eventually, the oxygen concentration in the atmosphere began to rise, fundamentally changing Earth's chemistry and paving the way for complex oxygen-breathing life. Every breath you take connects you to billions of years of biological evolution. Earth's internal structure is just as important as its surface conditions. Our planet has a layered structure, a thin, rocky crust, ranging from about 5 kilometers thick under the oceans to 70 kilometers under mountain ranges. A thick silicate mantle extending down about 2,900 kilometers, an outer core of liquid iron and nickel, and a solid inner core at the very center. Heat flowing from the interior drives convection in the mantle, and this convection in turn drives plate tectonics, the slow but inexorable movement of continent-sized pieces of crust across the surface. Plate tectonics is one of Earth's most important features, one that doesn't seem to exist in the same way on any other terrestrial planet. The crust is divided into about a dozen major plates and several minor ones. These plates move at rates of a few centimeters per year, about as fast as your fingernails grow. Where plates collide, mountain ranges rise up, and one plate can be forced beneath another in a process called subduction. Where they pull apart, new crust is created as magma wells up from below, creating mid-ocean ridges. Where they slide past each other, earthquakes occur along transform faults like California's San Andreas Fault. This constant recycling of crust is crucial for maintaining Earth's habitability. Volcanoes release gases from the interior, replenishing the atmosphere. Subduction takes surface materials, including carbon locked in limestone and other rocks, back down into the mantle. This geological thermostat helps maintain Earth's temperature over geological timescales. Without plate tectonics, Earth might have ended up like Venus, with a stagnant lid and no way to regulate atmospheric carbon dioxide. Earth also has a strong magnetic field generated by electric currents in the liquid iron outer core. This field extends thousands of kilometers into space, creating the magnetosphere, a protective bubble that deflects most of the charged particles streaming from the sun as the solar wind. Without this magnetic shield, the solar wind would gradually strip away our atmosphere, as appears to have happened on Mars. The magnetosphere also creates the auroras, the northern and southern lights. When solar wind particles that do penetrate the magnetic field interact with atmospheric gases near the poles, then there's the Moon. Earth is the only terrestrial planet with a large natural satellite, one that's about a quarter Earth's diameter. The Moon probably formed about 4.5 billion years ago, when a Mars-sized object called Theia collided with the young Earth in a glancing blow. The impact vaporized huge amounts of material, which then coalesced in orbit to form the Moon. This giant impact may have helped Earth in several ways. It knocked Earth's axis to its current 23.5-degree tilt, giving us seasons. The impact's energy may have helped differentiate Earth's interior, with heavy elements sinking to form the core while lighter materials rose to form the mantle and crust. And the Moon's gravitational pull creates tides in Earth's oceans, which may have played a role in the origin of life by creating tidal pools where organic chemistry could concentrate and evolve. The diversity of life on Earth is perhaps its most remarkable feature. From bacteria living in boiling hydrothermal vents on the ocean floor, to lichens clinging to Antarctic rocks. From sequoia trees 100 meters tall to microscopic plankton drifting in the oceans, from blue whales to beetles, life has colonized nearly every environment on Earth's surface. Estimates suggest there are somewhere between 8 and 10 million distinct species on Earth, though we've only formally described and named about 2 million. These species interact in staggeringly complex ways through food webs, nutrient cycles, and countless symbiotic relationships. Life doesn't just exist on Earth. It shapes the planet itself. Photosynthetic organisms created our oxygen atmosphere. Plants and other organisms play crucial roles in the carbon cycle, water cycle, and nitrogen cycle. Living organisms help create soil, alter the chemistry of rocks, and even influence climate. The idea that Earth is a self-regulating system where life and environment interact to maintain conditions suitable for life is called the Gaia hypothesis, named after the Greek Earth goddess. While the strong version of this hypothesis, that Earth is literally a living organism, is controversial, few scientists would dispute that life profoundly affects Earth's physical and chemical properties. From space, Earth appears as a beautiful blue and white marble, swirled with clouds, decorated with the browns and greens of continents. This view, the overview effect, has had a profound impact on astronauts who've seen it firsthand. They report feeling a deep sense of the planet's fragility, seeing how thin our atmosphere is, how interconnected everything appears, how arbitrary human-drawn borders seem from that perspective. As Carl Sagan famously described it after seeing a photo of Earth taken by Voyager 1 from the edge of the solar system, "That's here. That's home. That's us. On it everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. Earth is currently the only world we know that harbors life." the only world where intelligence has emerged to contemplate the cosmos. Whether life is common in the universe or rare almost beyond belief, Earth is precious. It's our only home, at least for now. And understanding how it works, how all its systems interact to maintain habitability, is crucial not just for scientific curiosity, but for our survival as a species. As we explore other worlds, we inevitably look back at our own with new appreciation. Earth isn't just another planet, it's the world that made us. And everything we know, everything we are, comes from this pale blue dot. Mars, the red planet that dreams of water. Mars glows in Earth's night sky with a distinctive reddish hue that has captured human attention since ancient times. The Egyptians called it Her-Desha, meaning the red one. The ancient Greeks associated it with Ares, their god of war, while the Romans named it Mars after their own war god. That blood-red color comes from iron oxide, rust-coating Martian rocks and dust. In essence, Mars is a rusty planet, and that rust tells a story of water, atmosphere, and dramatic environmental change. Mars is the fourth planet from the Sun, and the second smallest planet in the solar system, with a diameter of about 6,779 kilometers, roughly half that of Earth. Its mass is only about 1/10 of Earth's, which means surface gravity on Mars is just 38% what we experience here. If you weigh 100 kilograms on Earth, you'd weigh only 38 kilograms on Mars. A featherweight existence that would let you jump 3 times higher and lift weights that would be impossible on Earth. Mars takes 687 Earth days to complete one orbit around the Sun, giving it a Martian year nearly twice as long as ours. However, its day is remarkably similar to Earth's one Martian day, called a sol, lasts 24 hours and 37 minutes. From Earth, Mars looks like a small orange disk, even through powerful telescopes. But that disk reveals tantalizing features. Dark patches that early astronomers thought might be vegetation, polar ice caps that grow and shrink with the seasons, and occasional planet-wide dust storms that obscure the entire surface. In the late 19th and early 20th centuries, some astronomers, most famously Percival Lowell, claimed to see networks of straight lines crisscrossing Mars's surface canals, they said, built by an advanced Martian civilization to transport water from the poles to the arid equatorial regions. This sparked a worldwide fascination with Mars as a potential abode of intelligent life. The space age shattered these romantic notions. When NASA's Mariner 4 flew past Mars in 1965, returning the first close-up images of another planet, those images revealed a cratered, desolate world, more reminiscent of the Moon than Earth. The supposed canals were optical illusions. Mars appeared utterly dead, devoid of vegetation, cities, or any sign of life. It was a crushing disappointment to those who had hoped for a living world. But as more spacecraft visited Mars, a more nuanced picture emerged. Mars isn't dead, it's dormant. A world that was once far more Earth-like but underwent dramatic climate change that transformed it into the frozen desert we see today. The story written in Mars's rocks and landscapes is one of water, abundant water, in Mars's distant past. The evidence is everywhere once you know how to read it. Mars is crisscrossed with what appear to be ancient river valleys, complete with braided channels, tributaries, and features that look remarkably like river deltas. There are enormous outflow channels that seem to have been carved by catastrophic floods of unimaginable scale, releasing volumes of water many times greater than all of Earth's rivers combined, gouging channels hundreds of kilometers long and kilometers deep in a matter of days or weeks. The northern hemisphere of Mars sits about 4 kilometers lower in elevation than the southern highlands, and many scientists believe this northern plain once hosted an ocean covering perhaps a third of the planet's surface. More recently, rovers and orbiters have found even more compelling evidence. NASA's Curiosity and Perseverance rovers have found sedimentary rocks. Rocks formed from layers of sediment deposited at the bottom of ancient lakes and rivers. They've found rounded pebbles that could only have been shaped by flowing water. They've identified clay minerals that form in the presence of water. They've discovered organic molecules, carbon-based compounds, that are the building blocks of life as we know it. Development came in September 2025, when NASA announced that the Perseverance rover had found what they're calling a potential biosignature in a rock sample named Sapphire Canyon. The rock, nicknamed Chayava Falls, contains distinctive leopard spots, patterns of minerals arranged in a way that on Earth typically forms through biological processes. These spots contain vivianite and greigite, minerals that can form where microbes use chemical energy sources. The rock also contains organic molecules. Scientists are careful to emphasize that this is a potential biosignature, not proof of life. The same patterns could potentially form through non-biological chemistry. But it's the most compelling evidence yet that microbial life might have existed in Mars's ancient past. Confirming or refuting this finding is one of the primary goals of the Mars Sample Return mission, which aims to bring Martian rocks back to Earth for detailed analysis in terrestrial laboratories. So what happened? How did Mars go from a world with rivers, lakes, and possibly oceans to the frozen desert we see today? The answer lies in Mars's small size. Being smaller than Earth, Mars cooled faster. Its molten core solidified, shutting down the magnetic field that had once protected its atmosphere. Without that magnetic shield, the solar wind began stripping away Mars's atmosphere directly. Over hundreds of millions of years, Mars lost most of its atmospheric pressure. As the pressure dropped, liquid water could no longer exist stably on the surface. Water either evaporated and was lost to space, or froze and went underground or accumulated at the poles as ice. Today's Mars is a harsh, unforgiving place. The atmospheric pressure at the surface averages about 0.6% of Earth's, so thin that water would instantly either freeze or boil, depending on temperature, but could never exist as a stable liquid. The atmosphere is 95% carbon dioxide, with traces of nitrogen and argon. There's essentially no oxygen. Temperatures average around -60 degrees Celsius, though they can range from a relatively balmy 20 degrees Celsius at the equator during summer afternoons to a brutal -125 degrees Celsius at the poles during winter nights. Without a thick atmosphere, Mars's surface is exposed to harsh ultraviolet radiation and cosmic rays that would be lethal to any surface life. Dust devils and global dust storms occasionally scour the surface, kicking up the fine rust-colored dust that gives Mars its distinctive hue. These dust storms can be enormous. The 2018 global dust storm covered the entire planet for months, blocking sunlight so effectively that NASA's solar-powered Opportunity rover couldn't generate enough power and ultimately fell silent, ending a mission that had lasted over 14 years. Yet Mars still holds water, lots of it, just not on the surface. Both poles are capped with ice, a mixture of water ice and frozen carbon dioxide dry ice. The northern ice cap is visible year-round and contains enough water ice that if it melted, it would cover the entire planet to a depth of about 10 to 20 meters. Radar observations have revealed extensive deposits of water ice beneath the surface across much of the planet, particularly at higher latitudes. This subsurface ice represents a crucial resource for future human missions. Mars has two small moons, Phobos and Deimos, named after the sons of the Greek god Ares, Phobos meaning fear, and Deimos meaning panic. These aren't large spherical moons like Earth's. They're small, irregularly shaped, and heavily cratered. Phobos is only about 22 kilometers across at its widest, while Deimos is even smaller at about 12 kilometers. They're so small and so dark that they weren't discovered until 1877, despite centuries of telescope observations. Most astronomers believe they're asteroids captured by Mars's gravity early in the solar system's history. The landscape of Mars would be both familiar and alien to human visitors. While there are no forests, rivers, or cities, there are features that would impress even the most jaded terrestrial geologist. Olympus Mons, the largest volcano in the solar system, towers 21 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. Its base is so wide, about 600 kilometers across, that if you stood on its summit, the slopes would curve away beyond the horizon in every direction. You couldn't see the mountain's base, and if you stood at the base, you couldn't see the summit due to the horizon's curvature. Valles Marineris, a canyon system running along Mars's equator, stretches for 4,000 kilometers, roughly a quarter of the way around the planet. It's so vast that if it were on Earth, it would stretch across the entire United States from coast to coast. In places, it's 7 kilometers deep and 200 kilometers wide. By comparison, Earth's Grand Canyon is about 450 kilometers long and 1.8 kilometers deep. Valles Marineris makes the Grand Canyon look like a crack in the sidewalk. The question, was there ever life on Mars, remains one of the most compelling in planetary science. We know Mars had liquid water. We know it had a thicker atmosphere. We know it had energy sources, volcanic activity, hydrothermal systems, chemical gradients. On Earth, wherever we find liquid water and energy, we find life. Did the same happen on Mars? Or is there something special about Earth that allowed life to emerge here, but not there? If life did arise on Mars, it's almost certainly long extinct on the surface given the harsh conditions. But deep underground, where water might still exist as a liquid thanks to geothermal heat, perhaps sheltered from radiation in pore spaces within rocks, it's remotely possible that microbial life could persist. Future missions, including drills capable of reaching deep subsurface environments, may one day test this hypothesis. Mars also represents humanity's best near-term prospect for establishing a permanent presence beyond Earth. Multiple space agencies and private companies are actively working toward sending humans to Mars, potentially within the next 2 decades. The challenges are immense. The journey takes 6 to 8 months each way. The radiation exposure is severe. The thin atmosphere makes landing difficult, and there's essentially no oxygen, water, or food readily available. Yet Mars has advantages. Its day length is similar to Earth's. Helping human circadian rhythms, there's water ice available for processing the gravity, while low is enough to potentially avoid the health problems of zero gravity, and the soil could potentially be used to grow food in pressurized greenhouses. Mars captures our imagination because it's close enough to be reachable, yet alien enough to be exotic, familiar enough that we can envision humans walking on its surface, yet different enough that doing so would represent an epochal achievement for our species. It's a world that was once more like Earth, a reminder that planetary habitability can be lost. It's possibly a world where life once existed, or may still exist in isolated pockets. And it's potentially a world where humans might one day build cities under domes or underground, terraform its atmosphere over centuries, and make a formerly dead world bloom again. Whether that future comes to pass remains to be seen. But one thing is certain: Mars has more stories to tell, and we're only just beginning to read them. Solar system were a kingdom, Jupiter would unquestionably be the king. This gas giant is so massive that all the other planets combined could fit inside it with room to spare. More than 1,000 Earths could be packed into Jupiter's immense volume. Its mass is 2.5 times greater than all other planets combined. Jupiter is the 5th planet from the Sun, orbiting at an average distance of about 778 million kilometers, over 5 times Earth's distance. Yet it's often the second brightest point of light in our night sky after Venus, outshining even Sirius, the brightest star. Jupiter is fundamentally different from the terrestrial planets we've visited so far. It has no solid surface. Dive beneath its cloud tops and you'd pass through progressively denser layers of hydrogen and helium gas, eventually reaching regions where the pressure is so intense that hydrogen behaves like a liquid metal. Continue downward and the pressure would crush you long before you reached whatever lies at Jupiter's core, possibly a rock and ice core many times more massive than Earth, though we're still not certain. The planet's most iconic feature is visible even through small backyard telescopes: the Great Red Spot, an enormous anticyclonic storm that's been raging for at least 190 years, possibly much longer. Early telescopic observations from the 17th century noted a large spot in Jupiter's southern hemisphere. But whether that was the same storm we see today or a different one remains a matter of debate. A 2024 study analyzing historical records suggests the current Great Red Spot may have formed only around 1830, meaning the spot observed by earlier astronomers like Giovanni Cassini in 1665 might have dissipated, and a new storm formed later in roughly the same region. The Great Red Spot is vast, almost beyond comprehension. At its widest, it spans about 16,000 kilometers. Wide enough to swallow Earth whole with room to spare, though it's been shrinking. In the late 1800s, the spot was nearly twice as wide as it is now. Recent observations show it's not just shrinking but also oscillating in size every 90 days, expanding and contracting like a beating heart for reasons scientists don't fully understand. Recent data from NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, revealed that the Great Red Spot extends about 300 to 500 kilometers deep into Jupiter's atmosphere, far deeper than scientists expected and much deeper than the deepest parts of Earth's oceans. The winds in the Great Red Spot reach speeds of about 400 to 600 kilometers per hour, fast enough to tear apart any terrestrial hurricane. The storm persists because, unlike on Earth, there's no solid surface to slow it down through friction. On Earth, hurricanes weaken when they make landfall. On Jupiter, there is no landfall. Storms can persist for decades or centuries, drawing energy from Jupiter's internal heat and from smaller storms they absorb. The Great Red Spot is just the most famous of Jupiter's many storms and atmospheric features. The planet is wrapped in colorful bands running parallel to its equator, bright zones alternating with darker belts. These bands are massive jet streams, rivers of atmosphere flowing at different speeds at different latitudes. The zones are regions of rising gases and higher pressure, while the belts are regions of descending gases and lower pressure. The colors come from complex chemistry. The clouds are primarily made of ammonia, but trace amounts of sulfur, phosphorus, and organic compounds create the browns, reds, oranges, and yellows we see. We still don't fully understand what causes the various colors. The chemistry in Jupiter's clouds is extraordinarily complex and difficult to replicate in laboratories. Jupiter spins faster than any other planet in the solar system. Despite being more than 11 times wider than Earth, Jupiter completes one rotation in just under 10 hours. This rapid rotation causes Jupiter to bulge noticeably at its equator. If you could measure Jupiter at the equator versus pole to pole, you'd find the equatorial diameter is about 9,275 kilometers greater than the polar diameter. This rapid rotation also drives Jupiter's powerful magnetic field, which is about 20,000 times stronger than Earth's. Jupiter's magnetosphere, the region of space dominated by its magnetic field, is absolutely enormous, extending millions of kilometers into space. If we could see Jupiter's magnetosphere from Earth with our naked eyes, it would appear larger than the full moon in our sky. This powerful magnetic field traps and accelerates charged particles, creating intense radiation belts that would be lethal to unprotected spacecraft and humans. The Juno spacecraft had to be specially designed with a titanium vault to protect its electronics from Jupiter's radiation. The magnetic field also creates spectacular auroras at Jupiter's poles, far more intense than Earth's northern lights. These auroras are driven not just by the solar wind but also by volcanic material erupted from Jupiter's moon Io, which gets ionized and trapped in Jupiter's magnetic field. Jupiter has been extensively explored by multiple spacecraft, Pioneer 10 and 11 in the 1970s, Voyager 1 and 2 in 1979, the Galileo orbiter from 1995 to 2003, New Horizons briefly in 2007, and currently Juno, which has been orbiting Jupiter since 2016. Juno's mission was extended through September 2025, and the spacecraft continues to deliver breathtaking discoveries. In March 2024, Juno captured images showing Jupiter's tiny moon Amalthea, just 84 kilometers in radius, transiting across the Great Red Spot. Such images help scientists understand the complex three-dimensional structure of Jupiter's atmosphere. During 2023 and 2024, Juno also made close flybys of Io, Jupiter's innermost large moon and the most volcanically active body in the solar system. Io is constantly racked by volcanic eruptions driven by tidal heating. As Io orbits Jupiter, the planet's immense gravity flexes and kneads the moon's interior, generating enough friction to keep Io's interior molten. Juno detected a massive volcanic hotspot in Io's southern hemisphere larger than Earth's Lake Superior, belching out eruptions with 6 times the energy output of all human power plants combined. Over 400 active volcanoes dot Io's tortured surface, constantly resurfacing the moon and creating a thin atmosphere of sulfur dioxide that gets stripped away and replenished in a continuous cycle. But Jupiter's most fascinating moons are the other 3 Galilean satellites, so named because Galileo Galilei discovered them in 1610 when he pointed his primitive telescope at Jupiter. Europa, slightly smaller than our moon, may be the most likely place in the solar system to harbor life beyond Earth. Beneath its icy surface lies a global ocean containing more liquid water than all of Earth's oceans combined. This ocean is kept liquid by tidal heating from Jupiter's gravity. Recently, observations suggest that water occasionally erupts from cracks in the ice, creating plumes that shoot hundreds of kilometers into space. A future mission could fly through these plumes and directly sample the ocean below without even having to land. Ganymede, the largest moon in the solar system, even bigger than Mercury, has its own magnetic field, making it unique among moons. It too appears to have a subsurface ocean sandwiched between layers of ice. Callisto, heavily cratered and ancient, also shows evidence of a subsurface ocean. In fact, Jupiter's system could be thought of as a miniature solar system unto itself, with a giant planet at the center and a diverse collection of worlds orbiting it, some of which may harbor the ingredients for life. Jupiter has played, and continues to play, a crucial role in shaping the solar system. Its immense gravity acts like a cosmic vacuum cleaner, capturing or deflecting asteroids and comets that might otherwise strike the inner planets. Some scientists believe Jupiter has protected Earth from many potential impacts, though others argue this effect may be overstated. What's certain is that Jupiter's gravitational influence extends throughout the solar system, and it was likely instrumental in shaping planetary orbits during the solar system's formation. Jupiter also represents the boundary between the inner terrestrial planets and the outer ice giants. It's a transitional object, more massive than any terrestrial planet, but not massive enough to have sustained nuclear fusion and become a star. You'd need about 80 times Jupiter's mass for that. In that sense, Jupiter is a failed star, yet one that has dominated the outer solar system for over 4.5 billion years and will continue to do so for billions more. Observing Jupiter through even a small telescope is an awe-inspiring experience. You can see the cloud bands with your own eyes, watch the great red spot transit across the planet's face, observe the 4 Galilean moons changing positions from night to night, and occasionally witness a moon or its shadow crossing in front of Jupiter's disk. It's a view that connects you directly to Galileo's first observations over 400 years ago, to the centuries of astronomers who studied this giant world, and to the ongoing spacecraft missions that continue to reveal its secrets. Jupiter is a world that reminds us that our solar system is far more diverse and dynamic than early astronomers ever imagined. Saturn, the jewel of the solar system. If Jupiter is the king, then Saturn is the crown jewel of the solar system. While any planet is beautiful in its own way, Saturn possesses a majestic quality that's immediately apparent even in a small telescope. Those glorious rings, spreading out in a thin plane around the planet's equator, are one of nature's most elegant and surprising structures. No other planet's rings are as prominent or as intricate as Saturn's, and their presence transforms Saturn from merely another giant planet into something that seems almost too perfect to be real, as if deliberately designed rather than naturally occurring. Saturn is the 6th planet from the Sun and the second largest in the solar system after Jupiter. It orbits at an average distance of about 1.4 billion kilometers from the Sun, nearly 10 times Earth's distance. Like Jupiter, Saturn is a gas giant composed primarily of hydrogen and helium, with no solid surface. In fact, Saturn is so lightweight for its size that its average density is less than water. If you could find an ocean large enough, Saturn would float. Its rapid rotation, just over 10.5 hours for one day, causes it to bulge dramatically at the equator, even more so than Jupiter. Saturn appears noticeably flattened when viewed through telescopes. The planet's pale golden color comes from ammonia crystals in the upper atmosphere, mixed with traces of other compounds. While Saturn lacks Jupiter's bold, contrasting cloud bands, it does have atmospheric features. There are jet streams, storms, and occasionally large white spots that appear and fade over weeks or months. Saturn's winds are among the fastest in the solar system, with speeds reaching 1,800 kilometers per hour near the equator, faster than Jupiter's winds and far faster than any terrestrial hurricane. But let's talk about those rings, because they're Saturn's defining characteristic and one of the most scientifically interesting features in the entire solar system. The rings extend outward from the planet to a distance of about 282,000 kilometers, yet they're astonishingly thin, in most places only 10 to 100 meters thick. If you could shrink Saturn's rings down to the size of a piece of paper, that paper would be proportionally thinner than a razor blade. The rings aren't solid objects, but rather countless individual particles, each in its own orbit around Saturn. They range in size from tiny grains like dust to chunks as large as mountains. These particles are mostly water ice, which is why the rings are so bright. Ice reflects sunlight effectively. Some particles are pure ice, while others are ice mixed with rocky material or coated with organic compounds, but give parts of the rings a brownish or reddish tint. The ring system is divided into several main regions, labeled alphabetically in the order they were discovered, which leads to some confusing naming. The rings from innermost to outermost are D, C, B, A, F, G, and E. The brightest and widest are the A and B rings, which are easily visible from Earth through telescopes. Between them lies the Cassini division, a gap about 4,800 kilometers wide, discovered by Giovanni Cassini in 1675. This gap isn't empty. It contains ringlets and particles, but it's much less dense than the surrounding rings, which is why it appears as a dark band when viewed from Earth. In 2025, Earth-based observers will have an exceptional view of Saturn's rings as they approach an edge-on orientation with Earth, which happens roughly every 15 years due to Saturn's 29.5-year orbital period and its axial tilt. On March 23, 2025, the rings will appear edge-on from Earth's perspective. When this happens, the rings essentially disappear from view because they're so thin, revealing Saturn as an unadorned golden ball. This edge-on view also makes it easier to spot Saturn's moons, which are normally lost in the glare of the rings. The origin of Saturn's rings remains something of a mystery. For decades, scientists assumed the rings were ancient, formed when Saturn itself formed 4.5 billion years ago. However, data from the Cassini spacecraft, which orbited Saturn from 2004 to 2017, suggested the rings might be surprisingly young, perhaps only 100 to 400 million years old. This would mean the rings formed around the time dinosaurs were just beginning to dominate Earth. The evidence comes from the rings' composition. They're very bright and clean, primarily pure water ice with relatively little contamination from rocky material or organic compounds. Over time, the rings should get dirtier from impacts with micrometeoroids and from material falling in from Saturn's moons. The fact that they're so pristine suggests they're young. How did they form? Perhaps a moon ventured too close to Saturn and was torn apart by tidal forces. Perhaps a comet or asteroid crashed into one of Saturn's moons, shattering it. Perhaps two moons collided catastrophically. We don't know for certain, but what we do know is that Saturn's rings are spectacular, even more so up close. Cassini revealed that the rings are full of structures, waves, spokes, propeller-shaped features, and strange braided patterns in the F ring. These structures are created by gravitational interactions with Saturn's moons, particularly small shepherd moons that orbit within or near the rings and help keep certain ring sections confined. Saturn has 146 confirmed moons as of current catalogues, more than any other planet. Though many of these are tiny, irregularly shaped objects only a few kilometers across. Among the larger moons, two stand out as particularly fascinating: Titan and Enceladus. Titan is extraordinary, the second largest moon in the solar system, and the only moon with a substantial atmosphere. In fact, Titan's atmosphere is thicker than Earth's, with a surface pressure about 1.5 times that of Earth. This thick atmosphere is composed primarily of nitrogen, about 95%, with methane making up most of the rest. That methane is key to what makes Titan so fascinating. On Earth, water cycles through different states, evaporating from oceans, forming clouds, falling as rain, flowing in rivers back to the oceans. On Titan, methane does the same thing. Titan has clouds of methane, methane rain, rivers of liquid methane and ethane, and lakes and seas of these liquid hydrocarbons pooled on the surface, the only other world in the solar system besides Earth where stable bodies of liquid exist on the surface. Titan's largest sea, Kraken Mare, is larger than the Caspian Sea on Earth. The Cassini-Huygens mission revealed these features through radar imaging that could penetrate Titan's thick, hazy atmosphere. The temperature on Titan averages -179 degrees Celsius, cold enough that water ice is as hard as rock and forms Titan's bedrock. Organic compounds rain down from the atmosphere, accumulating on the surface as dunes of hydrocarbon particles that span hundreds of kilometers. Some scientists speculate that beneath Titan's frozen surface lies another ocean, this one made of liquid water mixed with ammonia. If so, Titan might have two distinct habitable environments: the surface with its exotic hydrocarbon chemistry, and a subsurface water ocean more similar to what we're familiar with. Enceladus, much smaller than Titan, offers a different type of excitement. This tiny ice world, just 500 kilometers in diameter, has geysers at its south pole that shoot plumes of water vapor and ice particles hundreds of kilometers into space. The Cassini spacecraft flew through these plumes and directly sampled them, discovering not just water but also salt, silicates and complex organic molecules including amino acids. These plumes come from a global ocean beneath Enceladus's icy crust, kept liquid by tidal heating from Saturn's gravity. The ocean is in direct contact with a rocky sea floor, meaning there are chemical reactions occurring similar to those at Earth's hydrothermal vents, precisely the kind of environment where life might arise. Many scientists now consider Enceladus one of the best candidates for finding extraterrestrial life in our solar system. Saturn has been visited by 4 spacecraft: Pioneer 11 in 1979, Voyager 1 in 1980, Voyager 2 in 1981, and most recently Cassini, which studied the Saturn system from 2004 until its mission ended in 2017, with a deliberate plunge into Saturn's atmosphere. Cassini's 13-year mission revolutionized our understanding of Saturn, its rings, and its moons, returning hundreds of thousands of images and gigabytes of scientific data. The mission's finale was deliberately chosen to prevent any possibility of the spacecraft crashing into and contaminating Enceladus or Titan, which might harbor life. Looking at Saturn through a telescope, even a small one, is one of astronomy's great pleasures. The rings are unmistakable, even in modest instruments. With patience, you can see the Cassini division and watch as the planet's axial tilt causes the rings to appear at different angles over the years. You might spot Titan as a bright star-like point near the planet, or catch glimpses of other moons. Saturn reminds us that the universe is capable of creating beauty on scales that dwarf human comprehension. structures so vast and delicate that they seem impossible. Yet there they are, real and magnificent. Uranus, the planet that rolls on its side. Uranus is weird. There's really no other way to put it. While every planet in the solar system has its quirks, Uranus takes peculiarity to another level. This ice giant, the seventh planet from the Sun, has an axial tilt of 98 degrees. To put that in perspective, Earth's axis is tilted 23.5 degrees from vertical, which gives us our seasons. Saturn and Mars have similar tilts. Neptune's tilt is 28 degrees. Jupiter's is only 3 degrees. Uranus? It's basically lying on its side, rolling around the Sun like a barrel rather than spinning like a top. Its axis of rotation is tilted so far over that it's nearly parallel to its orbital plane. This extreme tilt has profound consequences. For part of Uranus's 84-year orbit, one pole points almost directly at the Sun, experiencing 42 years of continuous daylight, while the other pole endures 42 years of darkness. Then, as Uranus continues in its orbit, the situation reverses. The equatorial regions have a more normal day-night cycle, but even there, the Sun takes a bizarre path across the sky, rising and setting in unusual directions and reaching different heights depending on where Uranus is in its orbit. The seasons on Uranus are like nothing we experience on Earth. Imagine winter lasting 21 years. What caused this extreme tilt? The leading theory is that during the solar system's chaotic early days, Uranus was struck by an Earth-sized object in a massive collision that knocked the planet onto its side. Computer simulations suggest such an impact could have occurred, potentially shattering Uranus's original moons and creating a debris disk that reformed into the moons we see today. Some models propose that Uranus was hit not once but multiple times by smaller objects, each impact contributing to tilting the planet further. Whatever the cause, Uranus has been rolling on its side for billions of years. Uranus orbits the Sun at an average distance of about 2.9 billion kilometers, 19 times farther from the Sun than Earth. At that distance, sunlight is incredibly faint, providing only about 1/400th the illumination that Earth receives. The Sun, as seen from Uranus, would appear as a very bright star, not the blazing disk we see from Earth. Uranus takes 84 Earth years to complete one orbit, meaning that one Uranian year is longer than a typical human lifetime. Despite being much smaller than Jupiter or Saturn, Uranus is still a giant by terrestrial standards. Its diameter is about 50,724 kilometers, making it roughly 4 times wider than Earth. Yet because it's composed primarily of ices and gases rather than dense rock, its mass is only about 14.5 times that of Earth. The ice and ice giant refers not to frozen water, but to compounds like water, methane, and ammonia that exist in solid or high-pressure fluid states in Uranus's interior. The planet probably has a small rocky core surrounded by a mantle of these ices, with a thick atmosphere of hydrogen, helium, and methane on top. That methane is responsible for Uranus's distinctive blue-green color. Methane in the upper atmosphere absorbs red wavelengths of sunlight and reflects blue and green wavelengths, giving the planet its aquamarine hue. Through telescopes, Uranus appears as a pale, featureless disk, quite boring compared to Jupiter's storms or Saturn's rings. For many years, scientists thought Uranus had a bland, inactive atmosphere. But appearances can be deceiving. When Voyager 2 flew past Uranus in 1986, the only spacecraft ever to visit this distant world. It saw a quiet, nearly featureless planet with only a handful of visible clouds. This led to the impression that Uranus was meteorologically dead. However, more recent observations with advanced Earth-based telescopes and the Hubble Space Telescope have revealed that Uranus actually has a dynamic atmosphere, with storms, clouds, and weather patterns. During the Uranian equinox in 2007, when the Sun crossed the planet's equator, massive storms appeared, some as large as continents on Earth. These storms come and go over hours or days, driven by unknown mechanisms in Uranus's atmosphere. Recent research has also revealed surprising details about Uranus's interior. In 2024, scientists announced that conditions inside Uranus might be conducive to forming superionic water ice, a strange state of matter where oxygen atoms are locked in a crystalline structure, while hydrogen atoms flow freely like a liquid. This bizarre form of ice could explain some of the peculiarities of Uranus's magnetic field, which is tilted 59 degrees from the planet's rotational axis and offset from the planet's center. Unlike Earth's relatively simple dipole magnetic field that resembles a bar magnet, Uranus's magnetic field is complex and chaotic, probably generated by convection in that superionic ice layer rather than in a molten core. Uranus has rings, though they're nothing like Saturn's spectacular ring system. Uranus's rings are dark, narrow, and faint. They weren't even discovered until 1977, when astronomers noticed them briefly blocking starlight as Uranus passed in front of a star. There are 13 known rings, most of them thin and dark, composed of particles ranging from dust size to about 1 meter across. The particles are likely fragments from moons shattered by impacts billions of years ago. The rings are so dark that they reflect only about 2% of the light that hits them, possibly because they're coated with organic compounds darkened by radiation. Uranus has 28 known moons, most of them named after characters from the works of William Shakespeare and Alexander Pope. Unique naming convention among planets. The 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, were all known before the Voyager 2 flyby. Miranda is particularly fascinating. Despite being only 470 kilometers in diameter, it has one of the most varied and bizarre landscapes in the solar system. Its surface is a patchwork of different terrains, old, heavily cratered regions adjacent to younger grooved regions, all jumbled together. One feature, Verona Rupes, is a cliff that drops about 20 kilometers 10 times deeper than the Grand Canyon. If you could somehow fall off that cliff in Miranda's low gravity, you'd take about 10 minutes to reach the bottom. The origin of Miranda's chaotic surface is debated. One hypothesis suggests that Miranda was shattered by an impact and then reassembled from the fragments, creating the mismatched terrain. Another suggests that tidal heating from gravitational interactions with other moons partially melted Miranda's interior, causing different regions to rise and sink in a process called cryovolcanism, involving water and ammonia instead of molten rock. In 2023 and 2024, astronomers using advanced telescopes discovered 3 new small moons orbiting Uranus, bringing the total to 28. These discoveries show that even now, we're still finding new objects in the Uranian system. And detailed study of these distant moons requires patience and advanced technology. Despite Voyager 2's flyby nearly 40 years ago providing most of what we know about Uranus, the ice giant remains one of the least understood planets in our solar system. There's currently no mission en route to Uranus, though the planetary science community has identified a Uranus orbiter and probe as a top priority for future exploration. Such a mission could finally answer fundamental questions. What's the internal structure? What drives the planet's strange magnetic field? What causes the atmospheric storms? Are the moons geologically active? Is there a subsurface ocean on any of them? Until such a mission happens, Uranus will remain largely mysterious, a tilted blue world rolling through the outer solar system, keeping its secrets. Neptune, dark blue jewel of the outer darkness. Neptune, the eighth and final major planet from the Sun, orbits in the cold, dark reaches of the solar system at an average distance of about 4.5 billion kilometers, 30 times Earth's distance from the Sun. At that remove, the Sun provides only about 1/900th the light and heat that Earth receives. Neptune takes 165 Earth years to complete a single orbit. Since its discovery in 1846, Neptune has completed only one full orbit around the Sun, reaching the same position in its orbit in 2011. If you had been born on Neptune, you wouldn't even be 1 year old yet. Neptune is slightly smaller than Uranus, but more massive, making it denser. Like Uranus, Neptune is classified as an ice giant, with an interior probably consisting of a rocky core surrounded by a mantle of water, methane, and ammonia ices under tremendous pressure. The planet's atmosphere, composed primarily of hydrogen and helium, with about 2% methane, gives Neptune a striking deep blue color, more vivid and saturated than Uranus's pale blue-green. That richer color comes from having more methane in the upper atmosphere, and possibly from unknown atmospheric compounds that enhance the blue hue. Unlike Uranus, which appeared bland when Voyager 2 visited, Neptune was a world of wild atmospheric activity. When Voyager 2 flew past in 1989, humanity's first and so far only close encounter with Neptune, the spacecraft found a dynamic, stormy world. The most prominent feature was the Great Dark Spot, an enormous anticyclonic storm in Neptune's southern hemisphere, roughly the size of Earth. Like Jupiter's Great Red Spot, this was a high-pressure system, though it appeared dark rather than light. Around its edges, bright white clouds of methane ice crystals formed and dissipated rapidly, whipping around the dark spot at speeds up to 2,400 kilometers per hour, the fastest winds in the solar system. But Neptune's Great Dark Spot wasn't permanent. When the Hubble Space Telescope looked at Neptune in 1994, the Great Dark Spot had vanished. However, a different dark spot had appeared in the northern hemisphere. Since then, multiple dark spots have come and gone, suggesting they're transient features rather than long-lived storms like Jupiter's Great Red Spot. We don't fully understand what creates these dark spots or why they disappear. The dark color might indicate holes in Neptune's methane cloud deck, allowing us to see deeper, darker layers beneath. Neptune's atmosphere exhibits strong banded structure similar to Jupiter and Saturn, with winds blowing in opposite directions at different latitudes. These winds are extraordinarily fast, the fastest planetary winds in the solar system, which is puzzling because Neptune receives so little solar energy. On Jupiter and Saturn, you might expect strong winds because those planets receive more sunlight and have substantial internal heat. Neptune receives almost no sunlight, yet its winds are even faster. This suggests that Neptune has a powerful internal heat source, radiating about 2.6 times as much energy into space as it receives from the Sun. The source of this internal heat remains somewhat mysterious. Unlike Jupiter and Saturn, which are slowly contracting and releasing gravitational potential energy, Neptune shouldn't have much leftover heat from formation. Perhaps the heat comes from ongoing differentiation in the interior, with heavier materials still sinking toward the core and lighter materials rising, releasing energy in the process. Neptune has a magnetic field similar in strength to Uranus's field and similarly tilted and offset from the planet's center. The magnetic axis is tilted about 47 degrees from the rotational axis and offset by more than half the planet's radius. This creates a complex, asymmetric magnetic field that wobbles dramatically as the planet rotates. When Voyager 2 passed through Neptune's magnetosphere, it detected strange radio emissions and intense auroral activity, though Neptune's auroras would be invisible to human eyes. They emit primarily in the ultraviolet and infrared. Neptune also has rings discovered in the 1980s. There are 5 main rings, named after astronomers who contributed to Neptune's discovery or study: Gali, Leverrier, Lassell, Arago, and Adams. The rings are dark and faint, composed of rocky particles mixed with organic compounds that have been darkened by radiation. The outermost ring, Adams, has an unusual feature: 5 bright arcs of material embedded within the otherwise uniform ring. These arcs, named Courage, Liberté, Égalité 1, Égalité 2, and Fraternité, are clumps of material held in place by gravitational interactions with Neptune's moon Galatea. Over time, you'd expect these arcs to spread out evenly around the ring, but somehow the gravitational shepherd effect keeps them bunched together. Neptune has 16 known moons, including 2 recently discovered in 2024. The largest and most fascinating is Triton, the 7th largest moon in the solar system. Triton is unusual in almost every way. It's the only large moon in the solar system with a retrograde orbit, meaning it orbits Neptune backward relative to the planet's rotation. This is a strong indication that Triton didn't form with Neptune but was captured, likely a Kuiper belt object that wandered too close to Neptune and got trapped by the planet's gravity. The capture process would have been catastrophic, potentially destroying any original moons Neptune had, and leaving Triton in a highly elliptical orbit that gradually circularized through tidal interactions. Triton is geologically active despite being one of the coldest objects in the solar system, with surface temperatures around -235 degrees Celsius. Voyager 2 observed active geysers on Triton, plumes of nitrogen gas and dark particles erupting from beneath the surface and rising 8 kilometers high before being carried downwind by Triton's thin atmosphere. These geysers are driven by a unique mechanism. Sunlight penetrates Triton's translucent surface ice, warming nitrogen ice below. The nitrogen vaporizes, building up pressure until it explosively vents through cracks in the surface. Triton's surface is young and diverse, with few impact craters, indicating recent geological activity. There are plains of frozen nitrogen, regions of water ice, strange cantaloupe terrain with intersecting ridges and valleys, and darker regions possibly composed of organic compounds. Triton also has a thin atmosphere of nitrogen with traces of methane. This atmosphere is slowly being stripped away by Neptune's magnetosphere and by the solar wind, gradually eroding Triton's mass over geological time. Because Triton orbits Neptune backward, tidal interactions between the two bodies are gradually slowing Triton down, causing it to spiral slowly inward toward Neptune. In perhaps 3.6 billion years, Triton will cross what's called the Roche limit, the distance at which tidal forces overcome a moon's self-gravity. When that happens, Triton will be torn apart, and the debris will spread out to form spectacular rings around Neptune, possibly rivaling or exceeding Saturn's rings in scale. Of course, this won't happen for billions of years, but it's a reminder that the solar system is still evolving, still changing, just very slowly from a human perspective. Neptune was discovered in 1846 through a combination of mathematics and observation. Astronomers had noticed that Uranus wasn't following its predicted orbit. There were small discrepancies that accumulated over time. Either Newton's laws of gravity were wrong, or there was another planet farther out whose gravity was tugging on Uranus. French mathematician Urbain Le Verrier and English mathematician John Couch Adams independently calculated where this hypothetical planet should be. When German astronomer Johann Galle pointed his telescope at the predicted location, there was Neptune, almost exactly where the math said it should be. It was a triumphant demonstration that mathematical physics could predict phenomena before they were observed. Neptune represents the outer boundary of the classical solar system. Beyond Neptune lies the Kuiper Belt, a region of icy bodies that extends from Neptune's orbit outward to about 50 AU from the Sun. This is where we find Pluto and the other dwarf planets, along with countless smaller objects, the frozen remnants of the solar system's formation. Neptune's gravity has strongly influenced the Kuiper Belt, capturing Triton, ejecting other objects into the inner solar system or out into interstellar space, and shepherding certain objects into orbital resonances. Some Kuiper Belt objects, called Plutinos, orbit in a 2 to 3 resonance with Neptune, completing exactly 2 orbits for every 3 of Neptune's. Neptune is a world we've only glimpsed briefly. Everything we know about it up close comes from Voyager 2's single flyby in 1989. In the decades since, observations from Earth-based telescopes and Hubble have added details, but we're still fundamentally ignorant about this distant ice giant. Questions abound. What creates the storms and winds? What's the detailed internal structure? How does the magnetic field really work? Is Triton's subsurface ocean real, and could it harbor life? What's the full inventory of Neptune's moons and rings? Answering these questions will require another mission, likely an orbiter that can study Neptune and its system over multiple years. Such a mission is challenging. The flight time alone would be over a decade, and operating a spacecraft in Neptune's cold, dark neighborhood requires advanced technology and power sources. But the scientific rewards would be immense, giving us a complete picture of this beautiful blue giant that marks the edge of the planetary realm. Dwarf planets and the outer reaches. The worlds beyond. When the International Astronomical Union redefined the term planet in 2006, creating the new category of dwarf planets, it sparked controversy that echoes to this day. The decision demoted Pluto from its status as the 9th planet, a position it had held since its discovery in 1930. Many people felt emotionally attached to the 9-planet solar system they'd learned about in school. But the reclassification wasn't arbitrary. It reflected our growing understanding of the solar system's architecture and the discovery of numerous Pluto-like objects in the outer solar system. The IAU definition requires that a planet must orbit the Sun, have sufficient mass to be round due to self-gravity, and have cleared its orbital neighborhood of other debris. Pluto meets the first 2 criteria, but fails the third. Its orbit is cluttered with other objects, and Pluto itself is just one member, albeit the largest currently known of the Kuiper Belt population. If we kept Pluto as a planet, we'd need to add dozens or hundreds more as we discovered them, or draw arbitrary lines about size that would be scientifically indefensible. Dwarf planets, then, are objects that are round but haven't cleared their orbits. There are currently 5 officially recognized dwarf planets: Ceres, Pluto, Haumea, Makemake, and Eris. But there are likely hundreds more waiting to be discovered or officially classified. Let's explore these fascinating worlds that occupy the twilight zone between planets and small bodies. Ceres is the odd one out, located in the asteroid belt between Mars and Jupiter, rather than in the outer solar system. It's the largest object in the asteroid belt, accounting for about a third of the belt's total mass, with a diameter of about 940 kilometers. Ceres was actually the first asteroid ever discovered, spotted by Giuseppe Piazzi on January 4, 1801, and it was initially classified as a planet. Over subsequent decades, as more asteroids were discovered, Ceres was reclassified as an asteroid. Now it's a dwarf planet, having come full circle in classification. NASA's Dawn spacecraft orbited Ceres from 2015 to 2018, revealing a world far more interesting than expected. Ceres has a rocky core surrounded by a thick water ice mantle. It contains more fresh water than all of Earth's lakes and rivers combined. The surface shows bright spots that turned out to be deposits of sodium carbonate, probably left behind when subsurface briny water percolated up through cracks and evaporated. These deposits suggest Ceres might have, or recently had, a subsurface ocean. Dawn also found organic molecules on Ceres's surface, though whether they were delivered by asteroids or formed on Ceres itself remains unclear. With water, organic molecules, and energy from tidal heating or radioactive decay, Ceres might meet the basic requirements for life, though whether it actually harbors life is highly speculative. Pluto, the most famous dwarf planet, has had a remarkable journey from obscurity to celebrity. Discovered by Clyde Tombaugh in 1930, after a systematic search for a predicted Planet X, Pluto was long regarded as a strange outlier. A small icy world with an elliptical tilted orbit that sometimes brings it closer to the Sun than Neptune. For decades we knew very little about it. Even the Hubble Space Telescope could barely resolve features on its surface. That changed dramatically in July 2015 when NASA's New Horizons spacecraft flew past Pluto after a 9.5-year journey across the solar system. The images and data New Horizons returned transformed Pluto from a pixelated blur into a real world with mountains, glaciers, possible ice volcanoes, and a hazy nitrogen atmosphere. Pluto's heart-shaped Tombaugh ratio became an iconic image. The left lobe of the heart, Sputnik Planitia, is a vast plain of nitrogen ice with a surface that's probably no more than a few million years old, constantly renewed by glacial flow and possibly by cryovolcanism from below. Pluto has 5 known moons. The largest, Charon, is so large relative to Pluto, about half Pluto's diameter, that the two objects orbit a point in space between them, making them almost a double planet. Charon has a distinctive reddish polar cap that might be formed by methane escaping from Pluto, being broken down by ultraviolet light and radiation, and then being captured by Charon's gravity. The smaller moons, Styx, Nix, Kerberos, and Hydra, are irregular chunks of ice probably formed from debris created when Charon formed, possibly from a massive impact in Pluto's early history. Pluto's atmosphere is thin but present, extending surprisingly far into space. It consists primarily of nitrogen, with traces of methane and carbon monoxide. As Pluto moves away from the Sun in its elliptical orbit, the atmosphere freezes and falls as snow onto the surface, only to sublimate back into gas when Pluto approaches the Sun again. This process creates seasonal changes on Pluto that occur over its 248-year orbital period. Haumea is one of the strangest objects in the solar system. Roughly the same size as Pluto, it spins so rapidly, completing one rotation every 4 hours, that it's been stretched into an elongated ellipsoid shape, like a squashed football. This rapid spin was probably imparted by a massive collision billions of years ago, the same impact that created Haumea's 2 small moons, and probably the family of similarly composed objects found in similar orbits. Haumea also has a ring system, discovered in 2017 when Haumea passed in front of a star. The first ring system found around a dwarf planet, Makemake, slightly smaller than Pluto, was discovered in 2005 and named after the creator god in the mythology of the Rapa Nui people of Easter Island. It appears reddish-brown, probably due to frozen methane and ethane on its surface. Makemake has one known moon, discovered in 2016. Observations suggest Makemake's surface temperature is about -239 degrees Celsius, cold enough to freeze nitrogen, methane, and ethane solid. Eris is slightly smaller than Pluto but more massive, making it the most massive dwarf planet known. Its discovery in 2005 was the catalyst that forced astronomers to finally define what a planet is, leading to the creation of the dwarf planet category. Eris orbits far beyond Neptune, taking 558 years to complete one orbit. At its most distant, it's nearly 98 AU from the Sun, almost 3 times Neptune's distance. It has one known moon, Dysnomia. The surface of Eris appears bright white, probably a coating of nitrogen or methane ice that freezes out of the thin atmosphere as Eris travels far from the Sun. Beyond these 5 official dwarf planets lie dozens of candidates awaiting detailed study and classification. Objects like Gong-Gong, Quaoar, Sedna, and Orcus are all round or probably round, and might eventually be designated dwarf planets. In early 2025, astronomers announced the potential discovery of a large trans-Neptunian object designated 2017 OF 2017 OF 2001, which could potentially become the 6th officially recognized dwarf planet if further observations confirm its characteristics. The Kuiper belt, stretching from Neptune's orbit outward to about 50 AU, contains millions of these icy objects, remnants from the solar system's formation. Beyond the Kuiper belt lies the scattered disk, where objects have highly elliptical and inclined orbits, probably scattered there by gravitational interactions with Neptune during the solar system's youth. And beyond that, extending perhaps halfway to the nearest star, lies the hypothetical Oort cloud, a spherical shell of trillions of icy objects, the source of long-period comets that occasionally fall inward toward the Sun. These outer reaches of the solar system are still being explored and understood. Questions persist. Is there a large Planet 9 lurking in the distant solar system, whose gravity is shepherding certain objects into unusual orbits? What's the full population of the Kuiper belt? How did these objects form and evolve? What can they tell us about the conditions in the outer solar nebula 4.5 billion years ago? Every few months, astronomers discover new distant objects, each adding a piece to the puzzle. These frozen worlds preserve a record of the solar system's formation better than the inner planets, which have been heated, melted, and geologically processed over billions of years. The dwarf planets and small bodies of the outer solar system are time capsules, holding secrets about where we came from and how our planetary system came to be. They remind us that our solar system doesn't end at Neptune. It extends far beyond, fading gradually into the interstellar void. The future, where exploration takes us next. We've journeyed through the entire solar system, from Mercury's scorched proximity to the Sun, to the frozen dwarf planets beyond Neptune. And we've only scratched the surface, quite literally, of what there is to discover. The exploration of our solar system is far from complete. Every mission returns more questions than answers, revealing complexities that earlier generations couldn't have imagined. So where do we go from here? What's next in humanity's exploration of our cosmic backyard? The near future of planetary exploration is full of ambitious missions, some already en route, others in development. Bepi Colombo will arrive at Mercury in 2026, giving us our first orbital reconnaissance of the solar system's innermost planet since Messenger ended its mission in 2015. The spacecraft will study Mercury's magnetic field, map its surface in unprecedented detail, investigate those mysterious polar ice deposits, and help us understand how Mercury formed with such an outsized iron core. Venus is experiencing a renaissance of interest. For decades it was largely neglected while Mars received the lion's share of attention. But that's changing. NASA has selected 2 missions to Venus Veritas, which will map Venus's surface in exquisite detail using radar, and Dia Vinci, which will send a probe through Venus's atmosphere to study its composition and take images during descent. The European Space Agency is also planning Envision, another Venus orbiter. India's space agency has proposed a Venus orbiter mission. This renewed focus on Venus reflects growing appreciation that understanding our sister planet is crucial for understanding Earth's climate and the evolution of rocky planets generally. Mars remains a primary target, with multiple missions planned. NASA's Mars Sample Return mission, developed in partnership with the European Space Agency, aims to retrieve the rock samples that Perseverance has been carefully collecting and caching on Mars's surface. Bringing these samples back to Earth for analysis in state-of-the-art laboratories could definitively answer whether Mars ever hosted life. The mission is technologically challenging. It requires launching a rocket from Mars's surface, rendezvousing in Mars orbit, and then returning to Earth. But it represents the next logical step in Mars exploration. Several nations are also planning human missions to Mars, with NASA targeting the late 2030s for the first crewed landing, though the timeline remains uncertain given the technical and financial challenges involved. The outer solar system moons are generating enormous excitement. Europa, with its global subsurface ocean, is the target of NASA's Europa Clipper mission, launched in 2024 and scheduled to arrive at Jupiter in 2030. Clipper won't land instead. It will perform dozens of close flybys using ice-penetrating radar and other instruments to characterize Europa's ice shell and ocean. The European Space Agency's JUICE mission, which launched in 2023 and will arrive at Jupiter in 2031, will study 3 of Jupiter's large moons, Ganymede, Callisto, and Europa, with a focus on Ganymede, where it will eventually enter orbit. Saturn's moon, Enceladus, with its active geysers venting material from a subsurface ocean, is another high-priority target. NASA is considering an Enceladus orbiter that could fly repeatedly through those plumes, directly sampling the ocean below without even needing to land. Titan, with its thick atmosphere and hydrocarbon lakes, is being targeted by NASA's Dragonfly mission, a nuclear-powered quadcopter designed to fly through Titan's atmosphere and land at multiple sites to study the moon's exotic chemistry. Dragonfly is scheduled to launch in 2028 and arrive in 2034. Uranus and Neptune remain frustratingly unexplored. The planetary science community has identified a mission to Uranus as a top priority for the next decade. Such a mission would likely involve an orbiter and possibly an atmospheric probe, studying Uranus's strange magnetic field, investigating its ice giant interior, and exploring its diverse moons. A similar mission to Neptune is also highly desired, but would likely come after Uranus due to the greater distance and travel time involved. Looking further ahead, more speculative missions are being conceptualized. These include probes to the Sun's gravitational focus point, where the Sun acts as a gravitational lens that could, in theory, provide incredibly detailed images of exoplanets. There are proposals for missions to the Oort cloud, missions to intercept interstellar objects passing through our solar system, and even missions to the Sun's polar regions to study areas we've never directly observed. Private companies are also getting involved. SpaceX's Starship, if successful, could revolutionize deep space exploration by making it economically feasible to send large payloads equivalent humans to Mars and beyond. Other companies are developing technologies for mining asteroids, establishing permanent bases on the Moon, and creating infrastructure for cislunar space. The line between government space agencies and private industry is blurring, potentially accelerating the pace of exploration. Technological advances will enable missions that are currently impossible. Ion engines and solar electric propulsion are making spacecraft more efficient. Advanced power sources like radioisotope thermoelectric generators and possibly small nuclear reactors will power missions to the outer solar system. Artificial intelligence and autonomous systems will allow spacecraft to make decisions on their own, crucial when communication delays to Earth can be hours long. New instruments will detect organic molecules, image surfaces through thick atmospheres, and penetrate ice to reach subsurface oceans. Perhaps the most profound shift will be in our perspective. The current generation of exploration focuses on robotic missions, spacecraft designed, built, and operated from Earth, with humans experiencing these worlds vicariously through data and images. The next generation will likely see humans physically venturing outward, first returning to the Moon, then onward to Mars, and eventually perhaps to the moons of the outer planets. When that happens, these distant worlds will transform from abstract concepts studied through telescopes into actual destinations where humans live and work. The questions driving exploration are becoming more focused on the possibility of life. Nearly every planned mission includes some component of astrobiology, searching for signs of past or present life, studying prebiotic chemistry, or characterizing habitable environments. The discovery of even simple microbial life beyond Earth would be one of the most profound discoveries in human history, answering the age-old question of whether we're alone in the universe. And if we do find life, even in fossilized form, that would suggest life is common in the universe, not a miraculous accident unique to Earth. We're living in a golden age of planetary exploration. Never before have so many missions been operating simultaneously, revealing so many worlds in such stunning detail. The images and data flowing back from Mars rovers, Jupiter orbiters, and Saturn missions would have seemed like science fiction just decades ago. Yet we've only begun to explore. The solar system is vast and we've visited only a fraction of its worlds. Each new discovery raises new questions, and each answered question reveals new mysteries. The story of the planets is, ultimately, our story too. We emerged from the same cosmic processes that formed these worlds. The atoms in our bodies were forged in ancient stars and assembled in the solar nebula. We're not separate from the solar system, we're part of it, products of its evolution, children of the cosmos. When we explore the planets, we're exploring our own origins, learning where we came from, and perhaps catching glimpses of where we might be going. So whether you're watching these missions from Earth, studying planetary science, or dreaming of one day traveling to these worlds yourself, remember that you're part of this grand adventure. The exploration of the solar system isn't just about science. It's about expanding the sphere of human experience, pushing the boundaries of what's possible, and satisfying that fundamental human urge to explore, to discover, to know. The planets have been there for billions of years, silent and waiting. Now, finally, we're beginning to read their stories, and those stories are more incredible than anyone imagined. If you've enjoyed this journey through our solar system, give this video a like and subscribe to Behind the Space for more deep dives into the cosmos. Hit that notification bell so you don't miss our next exploration. And let me know in the comments which planet fascinates you most, or which mission you're most excited about. The universe is waiting. Let's explore it together.